Hello, and welcome to our Energy and Environment webinar series, where we are very happy today to have Professor Anna Korre. She's Professor of Environmental Engineering at Imperial College and also the co-director for Energy Futures Lab. She's going to be talking about decoupling energy production and use from climate impact, a tale of many worlds. And this, the format of this talk is going to take around 40 minutes, and then we will be allocating the last 15 to 20 minutes to Q&A. In the meantime, if throughout the talk you have any questions, you can submit them to the Q&A box that you can see on the bottom part of your screen. And also during the Q&A session, you can raise your hand if you would like to ask directly to Anna. So with no more delay, Anna, the floor is yours.
Thank you, Nelia. I am delighted to be here to discuss about a topic that is very close to my heart, decoupling energy production and use from climate impact. I call this a tale of many worlds to entice a little bit your imagination and see how we come to the end of the talk with a discussion. I also thought that it might be interesting to know me a little bit. So I am Greek born. My family comes from a small village on the island of Naxos, which is in the middle of the Aegean Sea. You can see the village up there on the top left-hand side of the slides. And I grew up in Athens. I was born and grew up in Athens. And I went to university in Athens. And I joined Imperial College 28 years ago as a Marie Curie research fellow to do my PhD. I have had a fantastic time here and a lot of experiences out in the field, getting dirty, but I also clean up reasonably. The college probably thinks. The picture at the bottom right-hand side was taken last summer when we were doing a geothermal project fieldwork in Iceland. And just to talk a little bit about EDI, I still feel that there is a long way to go, and I hope that people like me and others like Nelia in other places will help and promote equality, diversity and inclusion culture at important universities in the UK. So today's discussion is going to be presented in three parts. First of all, I will discuss a little bit about the challenges, and I will draw somehow from my background in minerals, energy resources, and assessing the impact on the environment. And first of all, we are going to focus on local impacts and risks, and then we are going to look at global effects at operation and value chain level, using life cycle approaches, which is promised in the abstract you have read. And then towards the end, I hope that I will be able to debate with you what would take to decouple energy production and use from climate impact. So the local challenges. Many years ago, I was working on soil contamination and human health risk assessment. One of the case studies that we have done was looking at arsenic effects in soil and how they may have an impact on human health. And in those settings, what was actually quite important was to be able to assess whether there is an impact from the land use, and especially the human activities that might be different industries. In the case of Stoke-on-Trent, ceramics, minerals, metals, or waste disposal facilities, from important health impacts. So in doing those studies, we have been trying to see if there are correlations between soil contamination and, in this map that you can see on the right-hand side, incidence data for cancer, which luckily in this particular case, we have seen that they don't show a good correlation. I have also worked quite extensively on river water quality and ecological risk assessment. And here is an example from a study that we were doing in Chile, in a catchment called Cachapoal, south of Santiago, in the more Mediterranean climate of Chile, where we happen to have a lot of mining activity, as well as naturally high loads. Obviously, the pollution from the mining activity is something that we want to assess, and we want to make sure that while there is industrial activity, this does not affect the ecosystems all around. So with combining monitoring and modeling studies, we have been looking to actually distinguish between these impacts. You can see on the bottom right-hand side, the results on aquatic copper toxicity for the whole catchment, which is a huge area, as you would probably have appreciated from the previous map. And what you see in colorful red and yellow dots are areas where there is acute toxicity risk and correlates to an extent with the mining activities, and particularly at seasons where we have low flow, so during the summer period. So what I wanted to say by this is that actually the time that emissions occur is something that is important, and the regional context is also something that is important, and we have been considering quite extensively in studies that were following the impact of industrial activities at regional level. Currently, we are doing a lot of work focused on air dispersion of pollutants through combining emissions monitoring and modeling. And the couple of slides that I will show you here are for something that is a lot more relevant in our days. We are discussing about CCS implementation and post-combustion capture facilities. There is a small pilot at Ferrybridge power station, and using meteorological data and modeling, we have been looking to assess whether the emissions of amines in what is left after the capture process may degrade, and what levels of different nitrosamines and nitramines may reach the environment and may cause potential effects in different systems in the air that might affect human health and in waters that might affect ecosystems. In this particular case, the assumed maximum emissions would be below the regulatory thresholds for both air and water emissions. Now, this has been looking at local impacts, and normally we have good regulations that the industry has to comply with, and typically the environmental departments in industrial facilities work hard to make sure that compliance is achieved. There is a little bit of a difference, as you would imagine, between areas that are well regulated, like Europe, the UK, developed nations, and quite different challenges in places where there might not be as strict regulations available. But in the early days, we were focusing mostly on the local issues. But in more recent years, the global challenges and the value chain has become a lot more critical. So back in the early 2000s, I started working on life cycle assessment to actually be able to combine the work that we have been doing on assessing the environmental impacts of industrial activities at local level in the different environmental compartments, be it in soils, waters, or the air, and actually consider more global impacts like climate change, the greenhouse gas issues that every discussion is about at the moment with Glasgow going on. And also consider how the technosphere, which I call this cycle that you can see on the top right-hand side, actually works throughout the whole value chain and affects our planet. The life cycle principles are well developed and over the years, and we have an ISO standard. Many people have been working, producing consulting reports and doing studies, but in the last 3 or 4 years, I would say, there has been a flurry of activity, and especially currently. Now, my team at Imperial College has been working on life cycle assessment, developing a model that we call IC-LCA, IC for Imperial College, as you can imagine. And today I'm going to show you just the part that focuses on fossil fuel production, transport, and power generation, although other parts of it are looking at lithium-ion batteries and chemicals production, hydrogen, and all sorts of other things that I'm not going to be discussing today. So in fossil fuel value chain context, and especially if the focus is energy production, which we are discussing today, we have to trace back the emissions to the extraction of the natural resources, consider all the stages in the value chain that will affect the overall footprint of the system, and then also consider the possibility of capturing the CO2 as an important emission that we try to reduce, and also the infrastructure, which you can see in the purple-colored boxes at the bottom of the system. And this assessment is not just considering a process boundary and also a spatial boundary that might span continents in the case of fossil fuel value chains, but it also has a highly resolved temporal disaggregation, as you will see in a few minutes. So for this system, we focus on analyzing the performance of the system at 2 levels. The first part is to consider what happens at whole value chain level up to the point where the fossil fuel is delivered at the market, where it is going to be used for power generation or for other reasons. And then we also consider a system where the energy is generated and the CO2 that is produced is captured, transported, and stored if possible. For those 2 different value chains, the functional unit, as we define it in LCA terms, has to be different. So in the first case, an energy content of 1 megajoule of fuel delivered is what we use, which also allows us to compare different types of fossil fuel, for example, coal versus natural gas. And in the second case, we use the useful output of the process, which is the megawatt of electricity that is being generated. And I will have to talk about the advantages of our tool, and say why it is special and spectacular. It covers conventional and unconventional fossil fuel value chains, both for coal and for natural gas. It allows a very accurate accounting of fuels and materials that are being used, as well as emissions, also beyond just greenhouse gases to the different environmental compartments, and does so at unit process and subsystem level in order to be able to identify opportunities for emissions reduction. And because it has a modular structure, allows us to combine different component processes in a specific way that reflects the characteristics of any given value chain. So we can reconfigure our model to reflect any characteristics a value chain has anywhere in the world. We also have complementary elements to this tool, which focus on chemicals production, methanol, ammonia, for example. And we also have an equal resolution, same level resolution life cycle cost model that allows us to carry techno-economic and environmental optimization studies. So for our life cycle cost model, we have also integrated a real options assessment, which allows us to compare different opportunities and consider uncertainties and future evolutions for such a system. Now, of course, a lot of people are trying to do emissions estimation, and the standard way of doing this is to use generally accessible published emission factors. Now, an example of emission factors are listed in the table that I have there in the slide. And what is interesting, and I would like you to consider, is what uncertainty levels these emission factors are associated with. And you can see that the fraction of uncertainty in some cases is excessive. It's very high, which means that estimates can be very uncertain. If people are using the upper level of the emission factor, they may produce very high numbers, and sometimes different publications use those emission factors in a way that they try to justify certain objectives. Now, for our work, the aim is to provide evidence, and those evidence to be traceable and that in such a way that they can be tested. And depending on the level of detail that we have for a particular system, we can go away from the published emission factors at the very top of the table, all the way down to engineering calculations, process simulation, validation through monitoring, and the use of periodic or continuous measured data for key parameters that we are using to calculate emissions. Now, obviously, as we go down the list, we have to spend more time, and developing such tools has been a work of very many years. So the tools that I am going to show you today are the result of work in my research group for over 20 years. And it's not just one person's PhD study, mostly PhD pieces of work. And to illustrate a little bit what they are made of, so basically we have a high-level assessment, which for the natural gas supply chain looks like this, with elements that I hope are familiar to you, or not only on the infrastructure, but also the individual sub-processes. And if we dig further down into this, for individual boxes in the previous slide, we have particular modes of operation, and then depending on what exactly we are looking at, we may have process engineering models that are sitting behind the tool to actually provide estimations. And of course, this is going to be dependent on the data that we have available for each case study we are analyzing. But our models are already configured and validated with industry data, so it is quite reasonable for us to be able to adjust the parameters so that they fit the specifics of a given system. And just to explain how this becomes a complex exercise by taking an example from a natural gas production and transport value chain, we have a number of processes that might be involved. We consider a temporal domain, which is the lifetime of the considered facilities. We trace quantified environmental flows, and particularly for greenhouse gases, they are the ones that you would expect we are using. And we can do an assessment depending on the gate that we use of natural gas delivered at the market, or another gate if we have more than one gate, or megawatt power that is generated. And the same level of detail is valid for all the pieces of the models that we use in our tools. Now, this is not such a straightforward process, and I am trying to explain this by showing you the situation that we have in the North Sea, for example, where natural gas is produced in a number of offshore facilities, which are connected in a complex network, and the flows in between those nodes within the system might be complex, and they may also involve different products, like we may have gas as well as oil, and processing that occurs at different points in the value chain. Therefore, to be able to trace all this is quite a substantial exercise. And how we do it is by following this for specific facilities, analyzing the specific flows. So here you have an example of a real case study that we have analyzed that involves a number of wells that have different production characteristics, platforms that are connected which may also share some facilities, they may share some energy generation. So in order to do the analysis accurately, it is essential to follow the characteristics of this system. And of course, this exercise is time-consuming and detailed, but the reason why we do this is because we want to be able to trace where the emissions have come from, because the ultimate objective is not to punish those who emit. The ultimate objective is to help them identify where they can affect improvements in their system. And here you see a different example from another offshore platform operating in temperate oceanic climate, and how we're looking at the different emissions that may come from blowdowns, from venting, fugitives of different types, flares that may happen. Usually the combustion emissions are the ones that are quite easy to cope with and manage and understand. And at the end of such an analysis, we are actually able to allocate quite accurately both CO2 and methane emissions, which are the most important greenhouse gases that we have in natural gas value chains. And we can also estimate them for a period of time which will span the life of the facility, put an uncertainty bound around them. And the areas where you can see low level of uncertainty are usually the areas where we have had specific data from industry to validate our models and tag them accurately together. And here you can see an example of what an output would look like, looking at historical performance of such facilities and identifying where the different emissions are, but also projecting future emissions on the basis of production characteristics that the industry may expect. In other cases, this could be quite different. So the previous slide I've shown you was a mature site, whereas this one here we are looking at has quite a long life ahead of it for predicted emissions. And this one is tied with an LNG production, which is expected to continue for a number of years until 2054 before it is decommissioned. And what is actually interesting that you can see is something that sometimes bothers a little bit the industry. So the black dots that you can see on the graph are reported emissions. As you know, in Europe, we have to report emissions and facilities need to report them. And the engineers working for the companies need to do this accurately. It is quite useful that people like us work independently to calculate those emissions, and sometimes find that instead of under-reporting, they may also be over-reporting, as you can see by those blobbles that are floating above reality. And it is also quite useful to see how we can benchmark and how we can compare between different facilities. And I use this slide to show you some real case studies that we have done for one operator in the North Sea, who has a number of different fields in their control. And what you can see in the gray shaded area of the graph are reported values from studies that come from a number of different sources versus the actual results that we get for these case studies. And even for 2 different years, in the first round circle, you can see the same facility operating in 2014 and in 2015. And in the second, more oval-shaped circle, you can see a different a set of different fields which are part of the same system, but they function quite differently. So what I'm trying to say is that not everything is the same, and the differences are quite substantial. Maybe sometimes the true performance could be half of what might be in a neighboring facility. The one you can see at the very right-hand side of the graph also includes LNG, which involves liquefaction, and that you can see that it has a much higher footprint overall. So it is quite important to remember this. I will speak about LNG transport a little later. So the key learning from analyzing a large number of such case studies from around the world is that they do not perform the same, and they are very, very different. They could be orders of magnitude different. And here you can see at the top of the graph a number of different value chains which are based on offshore production with short pipelines, like the ones that we could possibly have if we have fields in the North Sea delivering natural gas to the UK, versus ones at the bottom of the figure, which might be looking at producing natural gas in different ways and involving LNG transport, for example, from North America or elsewhere to meet our demands here in the UK. And what is really, really unfortunate at the moment is that the price of the commodity that reaches our source, natural gas, does not really reflect that, does not consider the CO2 footprint. So a couple of years ago, we have been asked by industry, which is quite concerned and knows that this is an important issue, never mind the fact that they do not say a lot about it publicly, to compare a number of different global value chains. And here there are a number of real ones from different parts of the world. Some of them you can see are conventional and some of them are unconventional. Some involve transport via LNG and some involve transport via pipelines. And you will see that we split up for this analysis a European market versus an Asian market. In this comparison, it is the Japanese market, which imports quite a lot of natural gas. And what I want you to look at is the weighted average emissions on the basis of the fraction of the market that is served by different origins. And you can see how greenhouse gas emissions compare along the value chain. So you can see that for the European market, transport is as significant a component nearly as the production. And if you look at the Asian market, you can see that the upstream part, the production, is the most critical. Another quite interesting thing is methane emissions. And you might have heard President Biden making a commitment earlier this week to reduce methane emissions, which is, of course, quite an important progress. Here, for the same analysis at whole chain level, looking at the whole emissions, you can see in red 2.4% of produced natural gas that in North America is actually emitted as compared to 0.01, 0.2, 0.03 in other parts of the world. So there are good reasons why there is a focus on methane reduction, particularly in North America, mostly from shale gas operations. So what I'm trying to say here is in the red box, you can see at the bottom left hand side of the slide that identical products that may be manufactured in Europe versus ones that are manufactured in Asia or in China, they have a very different embodied carbon footprint. Let's say steel that is produced in China versus steel that is produced in the UK, or other commodities that are created in the different markets simply because of the source of the energy that they have, even if that energy comes from the same commodity. And this is very true for coal as well as for natural gas. And in this slide here, you can actually see a comparison between coal and natural gas. So the lower part of the graph, which you can read the energy production methods we have per kilowatt hour from different conventional, without CCS, and with CCS implementation. In cream color are the ones that are published in literature, and you can see there is quite a huge variation. And ones that are from our studies with a number of different companies in green. And you can see how variable the values are for coal. And what I wanted you to notice in this analysis is that when you actually implement CCS on natural gas, which you can see at the top part of the figure, this is not very much different than coal. So people like me who understand the data and have done a number of studies are not very much impressed when I hear during COP26 that the focus is on coal specifically. Ideally speaking, the focus should be on emissions reduction rather than focusing on specific commodities. And a few years ago, industry was a little bit nervous because they said, we don't have the tools how to estimate this. So my team has worked and developed a set of tools for industry so they can actually trace and identify the footprint of their different value chains, populate it with the data that they know from their own operations, and also predict emissions annually and into the future from the specific facilities, and consider all the different parts of the value chain. But this, of course, affects how GHG metrics work out and the economics. So here is the nervousness that people have in the markets, and I would like to discuss a little bit with you. So if you see what industry says, they will say, currently quite a lot of oil and natural gas is produced, and also quite a bit of coal. The majority of this ends up in the transport and industry parts of the system. And so far, the greener methods of producing energy, which are at the greener in terms of greenhouse gases, which are at the bottom of the pile there, they are basically used to supply residential, some commercial activities, and there is quite a substantial piece that you will notice of power loss from the transmission. Okay, so they recognize this, they understand it, and currently the focus is actually to shift the transport to other means. So we have all the push towards electrification, and there are these big questions about industrial decarbonization and substantial activity also here in the UK with the IDRIC Centre, where I am involved, to try to achieve a significant reduction in the greenhouse gas emissions from industry. But what the industry also says is that when they are trying to green their business, they say that they have a number of different commodities they have. And if they are asked to not only be responsible for the scope 1 and the scope 2 emissions, but also for the scope 3 greenhouse gas emissions, this exercise becomes quite complex. When I look at their materials, normally I have some concerns. And the first concern I have highlighted in the issues there in the box, which relates to carbon sinks or negative emissions, which they try to deduct from their emissions in scope 1 and scope 2, which I think currently is not done so very well. Then in most of the reports that industry produces, renewables are considered to have a net zero greenhouse gas contribution. And the other problem that these studies have is that the products that we have are not comparable at the endpoint use. So basically by life cycle assessment methodology test, they are not compliant. The other thing that they do, which is also a little bit less than appropriate, quite a lot less than appropriate, is that they have this midpoint equivalence adjustment that they do for the different products, which is incorrect. I mentioned in the previous slide. Another thing that they do is when they are minority partners with less than 20% share in operations, they typically don't account for that, which I don't think is sensible at all. And also when they consider the purchase of third-party products, which some of them actually manage within their refinery facilities, they actually exclude these from their assessment, which I think is not right. So when people are saying that industry is not doing enough, certainly I would say that probably they do a lot in the background, but when they are reporting, certainly not doing enough. But their key problem is that if they try to do greenhouse gas emissions abatement, they are faced with some challenges. They have some options which generally are good for their business. And you can see those in this recently published Chevron report, which are in dark blue color, which are of negative cost per ton of CO2 equivalent abated. But if you look at the options that are on the right-hand side of the graph, you will see that we have the renewable power, which is somewhat costly, a little bit, not very expensive, so it should be possible to implement. Then you have the forestry and agriculture and waste management industry that is okay for them because they can also consider as negative emissions. And then only then after that, CCS features and is quite expensive. So they are quite nervous about carbon pricing in general, which is what I have been advocating through my slides and telling you that the carbon should be costed in the price of the products. And this is because depending on the method that the policy is implemented, this might affect which abatement opportunities are the most cost efficient and might actually price them out of the market. So we have done a number of studies for a number of different value chains, and here I just included 2 examples to show you that the cost is quite variable. So if you look a little bit at this graph, you can see very few options that have a negative abatement cost, and some of the options that have quite a low cost, up to 50 or sometimes 100, up to 150, depending on the period that we use for the marginal abatement curve calculation. And for others, what you can see is that there is quite a lot that they can do at a very low cost, and then actually suddenly everything becomes a lot more expensive and even reaches a completely different scale, up to 400, 450 US dollars per ton of CO2 equivalent abated. Okay, so the different operators are in a different position, but they also are in a different market segment. And to illustrate this, I picked up some information from different sources for you to see what happens to the global daily oil production and where it goes around the world. So you can see how much China is importing, particularly from the Middle East. And what happens to LNG that goes around the world, again, with China importing quite a lot from the Middle East, but also from Australia. And in comparison to that, look at the bottom at what is the cost of their production. Okay, so the most cost efficient, the cheapest product you can get comes from Saudi Arabia, Iraq, Iran, Russia, the deep water non-OPEC countries, the ones who are resistant to implementing greenhouse gas emissions abatement. The ones who have already fallen off the market, the shale oils and the shale gas, actually, some of the shale gas, are not going to fall out of the market if something changes because people are good and they want to implement climate mitigation. It's because they are expensive. And that's why how carbon price is included in the assessment and how this is assigned becomes hugely important. They also appreciate quite a lot the business risk, which might to which they might be exposed due to the introduction of carbon policies that might affect whether they are in business or whether they have to come out of business. And they also report this internally. It's a very significant part of the business. Currently, the units that used to be part of the environment department in the past and look at greenhouse gas emissions have now gone into the finance offices of the big operators, simply because they appreciate this is a hugely significant business risk. So coming towards the end of the lecture, I just want to debate a little bit with you. What would it take to decouple energy production and use from climate impact? And here are my ideas. for you to consider. I think important things to address. Firstly, incentivize emissions reduction through innovation, cost reduction, optimization, and integration along the value chain. If a good performance is rewarded, then industry is going to have to do something, the same way that, as we have seen in Norway, a carbon tax, and the producers doing something to avoid those costs and be rewarded for their performance. The second thing that is essential is to improve transparency. And by improving transparency, I mean that we have to use engineering tools and monitoring to enable auditing, reporting, and performance comparison at operation and also at whole value chain level. And this is what we should be using as robust evidence to drive policymaking. So emotional pleas to not use wells coal in the wells steel making, or not use offshore natural gas that would be at very low carbon footprint delivered to the UK simply because we oppose the use of fossil fuels is, I think, is just communication stances. And the next thing that needs to be targeted is that we should generally reduce consumption. And this is something that has to be a pressure on us all, individuals as members of the society. Now, because not all products are same in terms of their greenhouse gas footprint, it is essential to make sure that the market value that products have reflects this footprint and therefore affects global competition. So if steel made in the UK can be made at a much lower greenhouse gas footprint than steel made in China, then we would not need to be offshoring our industry to China or other places. And the consumer is really the one who should pay the more. Then the next thing that I advocate is that we have to protect the planet, of course, and we need to be aware that this comes at a price, exactly like Prince Charles said at the beginning of the week. And we should be ready to shoulder this price because it is essential, but we should not aim to share this burden equally amongst the developed and the developing nations and amongst the rich and the poor in our societies. Developing nations who have not contributed to the global warming problems we experience today, they need to be given the opportunity to develop in a way that is sustainable and does not affect negatively the planet. And unless we actually support them, they will have no option but to use those resources that will make the problem worse for all of us. And finally, I think that we need to consider in an important way how we can implement tailored means to address local scale issues. And local scale issues, I mean issues of environmental protection. I was discussing about emissions around post-combustion capture facilities that may be collocated in a wider region, as well as economic impacts and skills development needs, or new skills or reskilling that might be necessary for workforce if things are to change. But these are, of course, my humble suggestions, and I only can hope that perhaps somebody is listening. So I look forward to any questions and comments that you have, and I hope that you found the talk interesting.
Thank you very much, Anna. It has been extremely interesting, and seeing so much data and actually data from industry. I can imagine that the collaboration must have been to put just this project in place, must have been huge effort from everyone working on it. If there is any questions, you can raise your hands if you want to just to ask directly to Anna. or you can use the Q&A box. I think that Kai, you had
Yes.
a question yourself.
Thank you very much, Anna. That's an absolutely important and timely talk, and also fascinating. I just want to know how you actually get the right amount of data, right? Amount of type of data, considering lots of the things are probably, company commercial confidential data, or some even organizational confidential data.
Yeah.
How do we approach that? Do we have to even to change the legal framework in terms of on a global scale?
Yeah, I mean, I think the data access is a very sensitive point. Like industry, of course, will not share data very easily, and will not share data that they feel their competitors may put their hands on, especially if this data will have a commercial value. Okay, so it is very hard. But my way of managing has been to convince people that we know what they are doing, and therefore they have been more willing to share. And normally what we do is we ask them to give us what they feel comfortable to give us. Then we actually provide outputs. And then when they find that the outputs are not to their taste, they actually have to provide more data and work with us to actually make sure that the information is correct. But as you said, it's not an exercise where this information can be shared out in the public domain. It has not been possible. So we have I must say I'm quite lucky that our team has been working on this topic for a long time, and we have a rich database of information. Sharing it is impossible. we are tied by confidentiality agreements. But the industry themselves, if they wanted to implement the methods, they have the data, they can use it. We just need to make sure that their reporting is robust, and we can verify that their reporting is accurate, and also monitor it in independent ways.
I see. So how do you envisage in future we are going to monitor or police how much CO2 is emitted by individual companies, for example? I mean, for example, a company that does produce everything using electricity. Now the company itself doesn't have anything to do with the, how the electricity was generated. It's all from the grid. Okay. So in that sense, how do we calculate?
Very easy to calculate. So you have a company that takes takes energy from the UK grid. We know what is the footprint of the UK grid on the basis of the allocation of the different energy sources in a given year. So it's very, very easy to do that calculation. And in China, it is also possible. In Japan, it is also possible to do an allocation. And although it is not in their control, the fact that they operate in that particular geographic environment means that they have a footprint. In the same way that when they operate in a particular geographic environment, the production costs are different. I mean, we are not policing that, but it is reported how much it costs to produce a barrel of oil in Saudi Arabia, and it is much lower than a barrel of oil in Canada. Yeah, so
and this changes all the time, right? This changes.
Yeah, it changes. Yeah, it changes all the time. Indeed, yeah, it changes all the time, and it changes all the time. I think that the annual reporting, like we do for all other emissions, how do we organize? In Europe, we had the Water Framework Directive and the Soil Directive and Air Pollution Directive, and we have been requiring companies to report. There is no difference in the pressure.
I see. My final question is that nowadays we talk a lot about hydrogen and ammonia as renewable, not renewable, carbon-free fuels. Have you done some analysis about that and how that can be made in sufficient quantity to have real impact?
Yeah, you used the word. Yeah, the quantity. So it's not, you're absolutely right that the method and the assessment of how energetically efficient the method might be is really meaningless until the point you have calculated and you have estimated the amounts that can be produced from the different sources. Yes, we have done some studies. And currently on current technology, hydrogen production by steam methane reforming is the cheapest method. So scaling up hydrogen use in different options can only be done through a stepping stone that involves fossil fuel. But one of my MSc students last summer was working on renewable hydrogen production for an industrial cluster in Spain, and comparing the footprints and looking at planning for the future in a 30 to 50 year time horizon. So we have already started doing studies like that. And other people, not just my group, I'm sure that other people are also doing studies.
Yeah.
It's a very interesting space. A lot of discussion is happening.
Sure. Yeah, thank you very much. Thank you.
I have a follow-up question, actually, because it has been very surprising to me that some industries, from the data shown, they were over-reporting the CO2 emissions. Is there a reason for that? Would they be benefited some way, somehow from that?
Yeah, of course. Sometimes we have to, you see, when people do independent studies, there is a way to verify how the calculations are made. So normally it is a methodological problem. Somewhere in the methodology, something that was not followed up properly. And I would say that until 4 or 5 years ago, life cycle studies within industry were limited. Usually they would go out to consultants and ask them to do a study, and they would do a very high level streamlined analysis. And those analyses might be a little coarse. So when they start using their own data, the values actually, I mean, they don't change. Once the method is ironed out, all the little problems and calculation methods are verified, then there aren't issues. But yeah, when the engineers saw the values, they were quite upset.
Which relates to my second question, because you were saying that it seems a bit subjective, like everything, they were not reporting anything under 20% or so.
Yes.
Are there no regulations for accounting for the amount of emissions? Or
this did not exist until now. So at company level, reporting has not been required. So normally they have to do reporting at operation level. And then for company level reporting, I mean, in their contracts, also, I don't know if you work on any contracts with industry, and if they are in joint ventures, when they are minority partners, they do not have the same access rights to information or anything else, and the same rules apply for this. So they say we don't have control, therefore we do not, we are not able to report. We don't know. They say we don't know. It's like here at the college at the moment, we are discussing quite a lot about our own carbon footprint. I don't know if UCL is thinking about this as well.
Yes.
Yes, about your own carbon footprint. And there is quite a lot of pressure by our academic teams to say that our carbon footprint should also include the shares that we own in a number of different companies. It should include all different types of activities, and what is inside the boundaries and what is outside the boundaries might affect the results.
Yes, it's been consistent throughout the whole process. That seems to be, as it is a new type of studies that are being taking place, it doesn't seem to be a global view on it, right?
Yeah, it needs a little bit of time. I think give it 3 or 4 years and everything is going to settle, because it's just like communicating the information, everybody looking at each other's results and saying, oh, this does not make sense. Like, for example, yesterday somebody gave me a report that came out of LSE talking about their travel footprint, and it is an inconceivably low number. So clearly, inconceivably low number.
Yeah, we need to set up some rules first. And it was also very surprising. Well, maybe it's because they have a lot of natural gas, but why for the US that they were so inefficient by using it? Is that because they have a lot, or because there is a culture of not trying to get to the maximum of what the fuel can give you?
No, I think it's because of their shale gas operations. So they operate above ground with a number of small wells, and the operations that they have to implement incur quite a lot of emissions. There are a lot of fugitive emissions because of the way that you have a lot of many points connected with a complex pipeline network. Whereas if you think about offshore production, say, I mean, in the North Sea, but also in other places, you can imagine there is a small number of platforms which connect to a small number of wells which are under pressure, and then come to a controlled facility which has to be operated with very high safety standards, because you cannot allow it to go up in the air if you have leak and conditions create explosions, or, you know, like 20-30 years ago, there were some accidents. When we eliminated the accidents and the control was good, then also the emissions went down for that reason.
Okay, so that's so they are in US. They are using techniques from a couple of well, not from a couple of centuries ago, but it's trying to adopt that system.
It's the type of resource as well, Nelia. It's like the type of resources they exploit. I mean, shale gas has been a revolution, actually reduced the price of natural gas substantially, and they flooded the market with natural gas at low price, and they picked up a big share. Quite a lot of other operations fell off the edge of being too expensive because suddenly there was cheap natural gas coming from the US to Europe. But their natural gas, the resource, they have to fracture the shale. They have to produce it from a large number of ways. So it's by design different.
It is, yeah. So yeah, I think that is consistency is what we need worldwide, because we seem to be very global for some things, but then for others, the know-how, it's there. It's trying to apply it. Can I ask you one last question? Sorry, I'm very interested in the topic that you have presented, and it's again regarding the different uncertainties in the emission factors that you were showing, the ones that had huge values. How have you been able to identify those? Because yeah, I'm assuming that the publications everyone is giving their values, and that is better for them. But then
those values are from US EPA and the Association of Petroleum Industries, API values. So the way that they generate them, they survey a number of different operations, and then they report the emission factors for the type of operation and the type of equipment. And depending on how old or how new it may be and the way that it is operated, there might be a wide range. And when one tries to pick up something from literature, which is not specific to the facility that they are studying, they will end up using a value that they don't know if it reflects the reality of that facility. But if you do a site-specific study where you actually have information from the specific facility, there are different rules that we can use. Like we know how many valves, what is the length of the pipelines in the plant, equipment counts that we use. And when we have everything specifically tied down, and we use statistics of potential leaks from such infrastructure, then it is possible to bring down those uncertainty factors quite a lot. And we have also seen that for new operations, like we have done some studies in cases like in Azerbaijan or in Oman, where the facilities are brand new. Industry likes to give us those facilities because they have very good performance. They're brand new. But if you compare this against other ones that have been there for a very long time, their performance would be quite substantially different. And what I suggest is that people should not be trying to focus on the industry as a whole, should be actually looking to identify which of those facilities do not operate efficiently and make the facilities so expensive because the carbon tax on them is so high that basically they have to go out of operation. It's not good if BP sells the site, and then a little operator tries to drive it like hell without concern for the greenhouse gas emission. It's not going to do good to the rest of us.
Totally agree. There are many problems to solve as engineers must take action. We have reached our time limit. It has been great to have you, Anna. Thank you very much for your time and for your great presentation, which will be uploaded to our website.
Thank you.
Thank you.
I'm very happy, and thank you for your questions and for the invitation. I appreciate it. Okay.
Thank you very much.
Thank you very much, Anna.
Bye, everyone.
Have a lovely afternoon. Bye-bye.
All the best.